Hi, hello, good day, everyone. My name is Inigo. I'm going to be presenting a topic related to digital twins. The title is Emergence of Digital Twins, and we're going to be talking about concepts, applications for digital twins, mostly related to design, manufacturing, and service. Well, before I would like to explain a little bit who I am and where I have studied and where I'm working currently. I'm going to also now shut down my camera, so I continue here. My professional career started in research at Datadriven Research Center in Finland, and before doing my masters and all that, I was working for different industries. To name few, they are Konecranes, Aalto, and also Nokia. And in Nokia, I started to work in digital manufacturing technologies and also 3D printing. But besides, I worked in academia, and currently after my PhD, postdoc, etc. Currently, I am professor at Tampere University in Finland, a professor in digital manufacturing. So the topics for today, it's related to digital twins, as I mentioned, and then I would like you to understand what it means digital twin, and also before that we're going to talk about model-based and data-driven engineering and the different differences and interlinks. I'm going to define what is a digital twin. We're going to talk about a digital twin with a product lifecycle perspective. I'm going to present some digital twin types and examples, some real cases, some toy cases, and we're going to end up having a summary of key concepts in digital twins. So the main sources are here, but across the presentation there are multiple references that you can follow up, and I will be sharing this presentation, I believe, so you guys are going to have a possibility to go deeper with the references on the literature. But yeah, before we get into digital twins, we need to understand what is the difference between model-based and data-driven engineering or data-driven manufacturing, as it is there written. We understand that conventional design and manufacturing is model-based. Traditional engineering is model-based, where experts gain experience by making physical observations. The experiences, together with human intelligence, derive in physical models using theoretical, experimental, and numerical methods. And we do this to better understand the mechanisms behind. So physics laws, the equations derived from measurements, it's regarded as model-based. However, in parallel, modern design and manufacturing is data-driven, in the sense that the data generated throughout the life cycle of a product, of a process, is used to enhance positively the system performance, fidelity, quality, and enrich the flexibility and autonomy of the system. So if we see modern engineering today, so model-based engineering goes through the cycle of observation, experiences, human intelligence, physical observations, and models. However, today we have sensors and technology who can record a process and generate data, use artificial intelligence or similar modeling techniques to make better decisions or smart decisions. So the key to modern engineering is to play your engineering activity in the middle. You're using model-based techniques and combining them with data-driven techniques. And what is digital twinning? What is a digital twin? If we look at modern companies, SMEs, large, they operate with a collection of mostly decoupled digital and physical assets. And to innovate in digital twins, we need to identify, explore business value-adding development activities that benefit from coupling and twinning digital and physical assets. So digitalization of manufacturing and digital twinning is crucial to find heuristic solutions to complex problems. So if we look at a company from R&D activities in the bottom all the way to the customer here, there are multiple physical and digital assets. And physical assets could be manufacturing systems here, like a plant where you have machines and sensors, etc. A digital asset could be full digital mockups, which could be operated here, and then you have multiple IT systems that try to couple these physical and digital assets all the way from the R&D activity to the customer. So I repeat, to innovate here, the important part is to explore and find business value adding development activities that benefit from coupling and twinning, or twinning those digital and physical assets. So digital twin was a term that it started to be generated around 2000, and the concept of digital twin was first proposed in 2003, as this reference explains. And today the research around digital twins and digital manufacturing and digital design tools, etc., has increased greatly. And from a formation stage, which was around 2000, nowadays we are at the growth stage. So nowadays, the concept of digital twins in research are related to manufacturing and production, engineering design, and prognosis and health management, also known as service applications. So mostly the share between applications is described here, where most of the applications of digital twins are related to prognosis and health management. Definitions, and it's important to define what is a digital twin, and there are several definitions flying around. And then the first ones that I recorded here, it's that it's a digital replica of a product or system maintained as a virtual equivalent throughout the lifespan of a physical product. Another definition could be a dynamic software model that uses sensors and other data to analyze its state, respond to changes, and improve operations. The key to digital twins is that you have a real physical space connected to a virtual space in which the data from the physical space is fed to the virtual space in exchange of information through models, or which could be model-based or data-driven models. But one of the first definitions of a digital twin was coined by NASA and the US Air Force in 2012, and the early adopters also were related to these kind of domains in aerospace and defense industry. And the definition explains that introduces that a digital twin is an integrated multiphysics, multi-scale probabilistic simulation of an as-built vehicle or system that uses the best available physics, models, sensors, sensor updates, history to mirror the life of a corresponding flying twin. Again, you have a physical, real space and a virtual space in which you have measurements fed into a virtual environment in which you do some control parameters and report, and you feed back with information to the real space. It is quite important to see a digital twin with a product lifecycle perspective. And the definition of a product lifecycle is that the specific product lifecycle is understood. It refers to the whole process from when we are generating a new product and a concept generation and design, when we are procuring those products or services, when we are manufacturing those, when we are using them, when we are reusing them, and when we are recycling. So digital twins can be applied to multiple areas of the product lifecycle. If we go to the topic of this presentation, I mentioned that we're going to be talking about digital twins in design, and I'm going to be presenting some examples of that. We're going to be talking about digital twin-driven product manufacturing, and we're going to be talking about digital twin driven product service. Again, the same definition: physics models fed real time by physical sensor data to mirror the life of its corresponding twin. So if we see here the classification of types of digital twins, we have digital twin driven product design, in which product design can be related to conceptual design, detailed design, or virtual verification. We might also have digital twins related to product manufacturing, in which we have digital twins related to physical shop floor, virtual shop floor, etc. And then digital twins related to product service, in which we for example could use real-time state monitoring of an application related to a machine. So this is the classification proposed by this reference, by this piece of literature, and I will give you some examples related to my work on digital twin product design. So for example, we can see here a drone and a structural simulation of a drone, in which we use the problem here is that when there is no product, how we can use real-time sensor data. And for example, we can do that by testing the interaction of a propeller and the forces and the boundary conditions that generate. So those forces can be recorded into a data set using a test rig, in which we are simulating the operating conditions of a drone. So we create a vast data set, a large data set, to connect that with a neural network. A neural network in this case is used to simulate as a regression tool RPMs, how fast the propeller is spinning as a function of efficiency, as a function of the vibration, as a function of the torque, and as a function of the thrust. Those are the forces that the propellers will generate on the structure of the drone, as it is simulated here in a simple example. We use artificial intelligence and neural networks here to absorb product and process variation, meaning that we tested multiple type of propellers. Precisely, we tested 3 type of propellers made of infiltrated carbon fiber, propellers made of polymer, ABS polymer, or propellers made of short fiber carbon fibers. We also tested multiple propellers to evaluate batch-to-batch variation, and then we also made multiple assemblies with different assembly torques to absorb this product variation. So using neural networks, we can create models that absorb and represent real-time operating conditions of the propeller. Then these neural networks are coupled with the structure of the drone, and we do a virtual design of experiment in which we can explore the whole design space. So here we also test different design variables. It could be related to geometry, thicknesses, materials, and so on. So it's not the same to have depending upon the mechanical properties of the structure of the drone, then the mechanical behavior will be different. So why we do this? So we do this to, for example, assess performance using surrogate models for structural resonances and numerical model analysis, structural stress and strain analysis, and other type of multiphysics. So for example, here we can evaluate different design solutions as a function of the resonance frequency and the maximum displacement, in which we can plot this as a function of the design variables. Here we can evaluate what is the most feasible design space. So this is a relatively simple yet complex approach of digital twins for engineering design. I will give you now another example of a digital twin related to product manufacturing. And here, for example, we have a conceptual machine of a direct energy deposition system in which is connected with a process chain of manufacturing activities, from DED, direct energy deposition of the parts, to machining, storage, treatments, heat treatments, etc., handling equipment. And then the idea here is that there is a factory integration in which the data generated throughout the process chain is stored and used by the digital twin to enhance and to make better decisions. Here are the parts, or exemplary parts. So the example, this is an example of a digital twin applied to larger scale additive manufacturing of metal components, and it is an example of a severe physical pilot line for serial production of high value components. It represents a digital workflow from design to manufacturing of a multi-stage direct energy deposition facility, and it has integrated multiphysics, data acquisition, modeling, predictive analytics, and inline quality control. Here, the data obtained in the physical world is used in the cyber world or in the virtual space to make, for example, trajectory recalculations of the manufacturing process due to thermomechanical distortions or strain, and enhance at the end of the day the process of the manufacturing system. Another example of a digital twin is here his additive manufacturing selective laser sintering process of polymers. This is a polymer machine in which we have sensors for infrared, heat, and also we have a system, a machine vision system, which is able to, for example, to evaluate the powder bed quality, in which we can detect if there is a low quality in the powder bed by a camera system. We also measure the powder at different stages and the quality of the powder using DSC, using SEM and particle size distribution measurements. And the idea is the same. So we use real-time, real physical measurements and models to, for example, simulate the powder and packing density of the powder in a physics-based simulation related to a manufacturing process of polymer parts. Last but not least, I mentioned also another application of digital twins related to product service. And when we talk about product service, this refers to maintenance and predictive maintenance applications. So this is, for example, an application related to machine prognosis and data-driven modeling of engine fault detection system. This is a ship which is remotely operated or remotely being operated, in which we have a system of multiple sensors which are able to record, for example, temperature in the filters and go close to the filters or close to the pumps. We can also measure pressure, etc. And all this data, it's then moved to a IoT edge data logger, in which all the data is stored in the cloud for later predictive modeling. So once the infrastructure is built, the machine is being operated in the middle of the sea, and we have the ability to take all this data from the engine system with an IoT data logger or an Internet of Things application. We take all the data to the cloud. Then this data can be used for example, statistical modeling and machine learning. So I repeat again, from the machine, data logger, cloud, database. Once the data is there, we need to do some pre-processing and cleaning up of the data, and then we can do feature extraction and statistical analysis and machine learning. So the application here is that this is time series in the horizontal axis, and and on the vertical axis is temperature of the machine. The blue line here, the blue line is the real operation conditions and temperature of. Yeah, as I was saying, the blue line is the real recorded temperature as a function of time, in which we can evaluate when versus the theoretical behavior, the physics-based model, which is the yellow line, and we can calculate, or we can have a threshold between the real sensor, real sensor temperature and the theoretical temperature, and use that to trigger an alarm for the system to be stopped, and to find out what's the root cause or the component having some sort of fault. Yep. And so in summary, and the idea of a digital twin again is that it consists of virtual models that are governed by physical laws. For example, in the case of a spring, based on Newton's law, force equals to the K, which is the constant of which is the constant of the spring, and X is the displacement or the compression. And then it's collected empirical data by sensors, which is used to create models or statistical models of the operating conditions of the spring. And it is consisted by two parts: the physics and the real-time data or real data. And this is used to, based on the collected real-time data, execute the virtual model in real operating conditions. And the idea is to correlate the virtual model and collected data to analyze past anomalies, ensure that the system behaves as expected, and predict future conditions of failure. So here you have the same idea in a visual manner. A spring is here, in which size, gauge, material, geometry, temperature, and environment has an effect on the behavior. And then the raw data would look something like that. What the physics law explains is that force in the vertical axis and compression in the horizontal axis, and the relationships explained by the law is a linear relationship, but we know that by variations in temperature, by variations in, for example, manufacturing defects, the behavior would be something different. So it would be non-linear, or would have some non-linearities. So the idea of a digital twin is that you can enhance a physics-based model by real-time measurements. Yeah, and what requires a digital twin? I mean, digital twin requires a non-trivial amount of modeling and computing resources. We need to know also that we need to understand that most products and systems are far more complex than what is possible to model and integrate into a digital twin. So creating a high-fidelity virtual model requires a deep understanding of the governing physical laws, as well as strong skills in computational engineering and physics and multiphysics. So the inherent complexities of a digital twin are difficult to understand fully, particularly when you consider the different type of twins in product design, in system engineering, manufacturing process planning, and in operation, as the service example we saw just recently. So building up a simulation of a product digital twin is not simple, but we talk about it very simply. However, the level of fidelity of the model is quite important. So the digital twin is supposed to be used in all sorts of simulations. However, the level of fidelity of the simulation, whether it needs to be high detail or lifelike versus higher level, needs to be defined. So to wrap it up, a digital twin is composed by a real space twin that you use to find explicit dependencies between input and output, hidden patterns, and also have predictive models to estimate outputs for the designs. The other part is composed by a virtual space twin to simulate the product real time with real operating condition with its governing physical laws and multiphysics. And typically we use in the virtual space we use multi-scale modeling techniques, using, for example, MATLAB Simulink, multi-body simulation, finite element analysis, computational fluidodynamics models, and other specialized simulation environments. We also need to understand that in the real space twin, typically we can have white box models, gray box models, and black box models, and the difference there is between the understanding of the behaviors of the input and output parameters. So for example, in white box models, we could be using single variable correlations or multivariable correlation, principal component analysis, surrogate models, and linear or nonlinear regression models. And also gray box models or black box models can be used, or artificial intelligence techniques like neural networks can be used to absorb variability in the manufacturing process or in the process of design, as the example we saw about the propeller and the structural integrity of the drone. So to finish it a little bit, multiphysics models in digital twins, systems are very complex, as I explained. There are thousands of critical parts that may require high fidelity and multiphysics models, and each critical part in turn is a part of a larger subsystem. So we could think that each subsystem may require its own digital twin. And then we also need to understand what is the difference between a model and a digital twin. So when we talk about models, often is validated by comparing to experimental data during the design development of a product, device, or process. May be connected to real device during operation and for control and system identification purposes, but often uses a very limited set of data. Whereas on the other side, digital twins is composed, as we explained, by a real and a virtual part, which are connected real time. And this is very important. Connection is real time, and it follows a device or process throughout its lifetime, from development to disposal, with this life cycle perspective from product, manufacturing, service, applications. It may contain and process vast amount of data and is not only used for modeling. In summary, and then to understand the purpose of a digital twin is digital twins are composed by physical and digital elements which are connected real time, and they can be used to describe and get visibility of a product, device, machinery, or a factory. We can interrogate the systems to discover problematic areas, analyze and design next generation of our system based on real-time data, as the drone example we saw, and artificial intelligence, analysis and design, as I mentioned, diagnostics, get online diagnostics. We can test what-if scenarios. So, for example, in a design process, we can predict. It might have a predictive use to predict failures, downtimes, material shortages, etc., and anticipate, perform corrective actions upfront. And this is pretty much what I wanted to talk in this about half an hour lecture or seminar recorded. And here is my contact information, and then I'm very happy to answer you any question or issues you may have. Thank you very much.